Morning people, welcome to the fifth lecture of MS 4603. So morning. So today we are focusing on this specific area beyond all the transistors and stuff like that. So in the first few lectures we have been focusing on the working principles of transistors, what is the effect of scaling and bringing these transistors close together, how do we prevent crosstalk between two types of transistors, what is a PMOS transistor, NMOS transistor, and things like that. Today we are going to talk about how we are going to build these metallization lines. Okay, so how these transistors are wired up to the outside world, and most importantly, how do you make sure these films are planar such that they can be connected up properly. Okay, so today's lecture we'll be talking about metallization. We have been mostly assuming aluminum as the metal line for a lot of the reasons, but now we have always almost all completely moved to copper interconnects for these locations inside the stack itself. We will talk about why this has happened. Then we'll talk about how do we actually go about patterning copper using this process called Damascene process, and then how do we planarize and why we need to planarize and things like that. Okay, and finally we'll focus on chemical mechanical polishing or chemical mechanical planarization. So the reason why one of the main components or one of the main motivations for making changes in metallization is this problem called electromigration. So I had referred to this in the tutorial yesterday a little bit. So this image is a more clear indication of what is happening during electromigration. So let's say we have this top electrode over here or a top metal line, and there is a voltage applied to it. This is the positive pole of the battery is this, negative pole of the battery is this one, and based on that there is a current flowing, and of course the electrons are flowing in the opposite direction of the electric current. Okay, so when the electrons are flowing in one particular direction, they have a kind of a momentum transfer between the electron and the ions. Okay, so electrons start to hit the metal ions inside the system and start to create vacancies at certain locations. Okay, so you would expect that normally in a wire and normally in copper wires that we see and we use in electricity everywhere, this effect should be happening. It may happen, but the probability of it is very low because the current densities are much smaller in the normal wires that we have. Current densities in a small thin metal line is much higher, orders of magnitude higher. Another problem that happens is that although in this image it looks very small, you literally have almost kilometer long interconnects within a chip. Okay, so you have so many multiple millions of transistors inside and they need to be wired up so much. You have kilometers of copper wiring interconnecting to each other. So at any point, if there is a defect that occurs due to electromigration, your device could fail. So electromigration as a phenomena has been studied for about 100 years, but the kind of conditions which promote electromigration is more or less seen in microelectronics. Okay, so the force felt by the ions is normally the direct force when you have an interaction with the electric field, and F wind, which is the momentum transfer effect. And the momentum transfer stuff starts to become important. And what it shows here is in that a big metal line, normally there is no problem. In a small metal line, you could have two kinds of defects. One is a void generation. So the fact that you have all these vacancies being created, they can build up together and actually literally break the material apart. Or you could have stuff popping out because there is a redistribution of the material systems, right? At certain places it will break, at certain places it will pop up. So this can be clearly seen in a simple video here. So this is a gold line of a gold nanowire and of a two thin gold contacts, and in the middle over here you can see that the cross section of the gold is very small, so the current density at that locations will be very high. As you apply voltage and current starts to flow through it, so this is a scanning electron microscopy done in an in situ manner. You will slowly see that in a way it is a bit fast because it's a few seconds. You can see that there's a defect being created and the whole thing breaking apart. Okay, so materials are physically breaking apart primarily because of the fact that there is high current flowing through the system. So in a way, people take advantage of the fact that this kind of a break can happen by trying to grow nano gaps and things like that out of it, and then trying to do fancy measurements by putting molecules in between these gaps and things like that. But for the case of microelectronics, it's a problem. The opposite effect is the hillock growth. So this is a flat part of a metal line, and as current passes through it, you will see a hillock growing out of the line. Okay, so high currents passing through it and the materials redistribution caused by the high currents passing through it can literally change the shape of your metal lines and cause defects. So if the hillock is being formed and there is another layer sitting on top of it, it can lead to defects. Okay, so this is the logic of electromigration. So electromigration was a major problem for aluminum based metal lines, and the way you characterize electromigration is using this kind of equation. So this you may have learned in your quality control course. So it says, so let's say you are comparing multiple metal lines, okay, of a particular factor, of a particular dimension. The median time to failure, which is the time taken for 50% of the test samples to fail, is proportional to the current, inversely proportional to the current density, temperature, and the activation energy. Okay, so because of the fact that it is a kind of a random phenomena, you can it's best to define the failure rate based on this. So immediately you can see that as you increase your current density, the amount of failure should increase. So it should be faster and faster for the median time. So MTF will reduce. So it gets faster and faster for the defects to fail. And of course, activation energy, if you can make activation energy higher and higher, your MTF will increase. That means it will take longer time for these devices to fail. Okay. So current density is a bad idea. And the reason why we have only a proportional sign and this is because there are other factors involved. These factors can be determined primarily by the kind of grain size, the kind of grain orientation, and how much distribution of the grain size you have. Now the reason why grain size is important is because activation energy for diffusion within the bulk of a grain and at the grain boundaries are very different. Okay, so in the bulk of the grain, when you are talking about electromigration and the diffusion of atoms, the activation energy is higher. But over here, grain boundaries are the locations where metal atoms are not bonded properly, right? There is a discontinuity in the packing of the material. So the activation energy for diffusion at the grain boundaries is very high. Another factor that is also important is that the wind, when it is passing through the bulk of the lattice, the amount of interaction between the electrons and the lattice is not that much of a problem. It's just over here where there is asymmetry and there is discontinuities, the amount of electromigration effects are also felt higher. Okay, so if you increase your grain size, of course the number of grain boundaries are less, and therefore you have less problem. And in case of some 1-1-1 preferred orientations, they have been experimentally shown that they have less electromigration effects. Okay, so in this case, again you need to understand that MTF is the median time to failure. So in a way, it is a time required before a void grows or a hillock grows and discontinues the whole current flowing through it. Okay, so in this case, you can see, okay, there's a lot of grain boundaries, you'll have a lot of electromigration, but the width of the wire is pretty high, so current density is less. Here, of course, you would expect it to be worse because the current density is much higher now, and therefore grain boundary, therefore electromigration effects are higher. In this case, as you go smaller, actually a reverse effect starts to happen. In this kind of a structure called the bamboo kind of structure, you can see that the grain boundaries completely bridge the wire, or the wire width is smaller than the width of a grain boundaries. At these kind of conditions, the resistance to electromigration actually goes up because the voids are not able to combine together, and the vacancies are not able to combine together and form a big void. Okay, so over here, as current flows, voids, and voids are created at this junction, and this can lead to a growth and break your whole wire. Well, over here there is more resistance to grain growth, more resistance to void. So this kind of a bamboo structure has been seen to be more resistant to electromigration. The problem though is that for these kind of conditions to happen, you need to make your wires very, very small, and therefore the resistance of the wire itself can go up. So although this phenomena has been noted, in order to take advantage of this phenomena, you need to do a lot of redesigning of your circuitry to make sure very low current flows through it, etc. Okay. So this is a big problem of electromigration seen in all metals, and this was more apparent for aluminum, which had activation energy of lattice diffusion, which is smaller than that of another metal such as copper. Okay. So this is the activation energy. The smaller activation energy, the easier for it to diffuse and break. So you can see that copper has better effect than aluminum. Therefore, initially when aluminum was utilized and aluminum started to fail, you added a bit of copper into the aluminum to increase the electromigration resistance. Okay. So this is what was referred to in our tutorial yesterday, whereby which copper sits at the aluminum grain boundaries and improves the electromigration resistance. But eventually we have almost completely ditched aluminum and moved to copper, primarily also not because of the fact that electromigration is better for copper, or electromigration resistance is better for copper. Other advantage is, of course, copper is much more conducting than aluminum. Okay. So because of these reasons, we have moved from copper to aluminum. In addition to electromigration based effects, another problem you need to worry about is stress voiding. So in this particular case, even if there is no electromigration or current flow, just the fact that you have thermal effects or heating and cooling, and there is a mismatch in the thermal expansion coefficient, can also lead to stress voiding. Okay. So this can generate impurities or defects or dislocations at the interface, which can grow together, become voids, and lead to failure as well. Okay. So this stress voiding is also a problem in many of these material systems. All right. So when moving to copper, because of the fact that copper is much more conducting and also has lesser problems associated with electromigration, we need to figure out how to pattern copper. So this patterning of copper is a problem because the logic of etching or the logic of patterning is that you convert the copper metal or the material you are etching into a soluble compound or into a gaseous compound. If you are doing wet etching, so in this case, let's say you start with a positive pattern on top of the photoresist. Let's say we are etching aluminum, let's say. Okay. We keep the photoresist blocks the etchant from attacking the aluminum below it, and then when you remove the photoresist, this is the pattern on the photoresist has been transferred onto aluminum. Okay. And then you can deposit and planarize and things like that. But basically, if you are etching aluminum over here, when we are utilizing an acid to etch aluminum, that acid is converting aluminum into something which is soluble and washes it off, if you are using liquid etching. If you are using gaseous etching like the plasma etching we learned in 3012, the gaseous reactants are, after the gaseous reactants have reacted with the metal, it is also easy to go off. Okay. So the byproducts are also soluble, or not soluble but gaseous and goes off. This is not a problem. This is a problem in chlorine, because let's say you are using hydrochloric acid to etch chlorine, it will become copper chloride, but copper chloride is not so easily dissolved. So copper chloride residue can remain over there and can contaminate your system. Similarly, with gaseous etching also, you cannot really convert copper to a gaseous compound. It stays there. Because of that, we have to utilize another type of way to pattern copper. Okay. And this particular process is called Damascene process. So in the Damascene process, you again start off with the photoresist patterned. The key factor to notice here is, over here when it is a positive pattern, here it is a negative pattern. We etch trenches into the dielectric and form holes within the dielectric. deposit the metal, mostly copper, inside it, and then we CMP and etch away or polish away the layers standing outside. Okay. So, we fill in the copper and polish it off, and then finally after you have polished it off such that the copper is only sticking over here, you deposit another layer and encapsulate it. The final result is the same between the left and the right. The difference is that this is a kind of an additive way of patterning the copper. You are inlaying the copper within the gaps within the SiO2, and that is why you have this process of demassing. So, you do not etch the copper, you don't cut off the copper in this particular manner, you fill in the copper within the gap. Okay. So, this process was developed by IBM, and it was very revolutionary because people had been trying to figure out how to effectively pattern copper in an efficient manner such that there is no impurities and things like that. Okay. So, basically the concept is you need to etch the path in the dielectric and then fill it up with the metal, okay, rather than depositing a metal film and then patterning the metal. Okay. So, that is from the Damascene process is the case when you do it for just one single layer. You could also do advanced stuff called dual Damascene, whereby which you etch two patterns. This is a via, this is a trench. Both a trench and via are patterned together, and then we have one step to fill in the whole stack with the metal. Okay. So, that is illustrated over here. So, if this is the way you would do it if you do a normal process. A normal process here where you are doing 2 times Damascene process, you again have the initial devices. Let us say this is the source and the drain of a transistor, the contact of the source and drain. You deposit your dielectric, you make holes in the dielectric. After patterning it, you fill it up with tungsten or copper, then you pattern it away or you CMP it, then you grow another layer of metal, then you put photoresist, then you pattern it, and after you have patterned and received the aluminum, you again grow a dielectric in the middle of it. This is how you do 2 layers of this material. To be more efficient, this is the dual Damascene process. So, this process is summarized over here. So, let us focus on this one. In the case of the dual Damascene process, you have a very critical usage of the etch stop layer. So, you have the silicon oxide over here. So, if you want to form a Damascene process, you first put an etch stop layer, then you grow your SiO2 where you want to form your via. You put a second etch stop layer, again an SiO2 on top of it. Okay. So, you have 2 types of etch stop over here. An etch stop, if you remember from 3012, is a kind of layer which improves the selectivity of etch dramatically. So, let us say you are etching through the SiO2, the etch stop layer, in this case may be silicon nitride, will be very resistant to the material used to etch the SiO2. So, let us say you are using hydrofluoric acid to etch the SiO2. When the hydrofluoric acid reaches the etch stop layer, it stops etching because the chemistry does not work. Okay. So, by using 2 types of etch stop layers, we start off, we form the trench layer, then we strip off the silicon nitride, we pattern one more layer below it such as it is the via, and once both the trenches and the via are done, we fill it up with copper. Okay. And the copper is deposited through a process of electrode deposition, details of which Prof. Puisi will talk about in the future. Okay. So, this is the way in which instead of doing 2 times of patterning, more number of filling up the layers and starting one by one, here you start to condense it and try to combine the number of processes together. So, this is called the dual Damascene process, whereby which you fill in a trench and a via at the same time. People do a lot of variation of these kind of processes, but effectively you are trying to fill it up in a very nice manner. And the reason why we use, so this is again the same illustration of the dual Damascene process, and the reason why we use the process of electrode deposition is because you can see that finally you have to fill in a trench and a via. If we are going to use sputtering or any other physical vapor deposition kind of process, there is a high probability that you won't be able to fill in the gap completely, because the sputtering atoms are going to come from the top, etc. So it won't be able to, it may not be able to fill in the whole thing completely. Okay. So we use this electrode deposition process, which will start from the bottom and slowly start to fill up. Okay. So before you can do electrode deposition process, you need to put a thin seed layer of copper above it, and then you deposit inside the solution and electrode deposition starts to happen. Okay. Prof. Puisi will be speaking in more detail about the electrode deposition process, the kind of additives utilized in the solution, etc. So this shows you the different types of etch stop, etc. utilized to form the patterns. So copper, as I told you, we use copper because of the fact that copper has better electromigration resistance and is also much more conductive. But the problem, one of the problem it has is that it's harder to pattern copper. So we have to do Damascene process. There are other problems with deposition of copper. It's very hard to sputter and form deep trenches. So we deposit it using electromigration through electrode deposition process. So that is the second difference. The third difference that is actually not shown here very clearly is that we have no choice but to put a layer between the copper seed and the other material. So there would be a tantalum nitride or a tungsten nitride layer between the insulator and the copper seed layer. That has two roles. One, of course, is to improve adhesion and things like that. The second problem is that copper can diffuse. So copper can actually diffuse into silicon and silicon oxide very nicely if you heat it up too high. So in order to prevent the copper from diffusing into the insulator or into the underlying metals and things like that, you need to put a diffusion barrier in between. So the advantages of copper are electromigration resistance and conductivity improvement. But in order to bring copper into this, you need to develop a new process, Damascene process, to pattern it. You need to make sure you deposit to electrode deposition processes, which was not so common at that time. And thirdly, you also need to make sure you have a diffusion barrier to prevent copper from diffusing into the rest of the system. Okay. Copper is a kind of a messy material, so when these kind of processes were coming out, people had a copper-based foundry or a copper-based clean room, which is separate from the other clean room to prevent copper contamination and things like that. Because of the fact that copper can diffuse everywhere, they literally keep everything separate. Once a wafer has gone into the copper foundry, they would not be even allowed to be brought into the non-copper foundry and things like that. So even nowadays, some people are extremely careful with copper in the normal conventional process, just because copper can diffuse and change the process of the silicon, change the electrical properties of the silicon dramatically. Okay, so this is an example of multi-layers of copper that are being formed such that you can see that, so over down here is all your transistors and things like that. And these are the different, since it's a cross section, you cannot really see all the intricacies of it because there are multiple transistors within the plane of the screen. So this is all the different connections, dual Damascene processes, etc. utilized. So you could have up to 9 or 13 types of metal layers being built up one by one. We will see later on a process flow on how you would build up a couple of these layers. Okay. So, copper Damascene process is very important and copper is a very heavily utilized material for metallization. The other concept very important for metallization is surface planarization. Okay. So on the left over here is a transistor, it's a device that we are building. So below here are our transistor, this is our locus. As you know, locus has the bird's beak, it has this kind of a shape. So there is a height discontinuity. Okay. Let's say you have a metal line running on top of this field oxide and you have this PMD, which is a pre-metal dielectric deposited on top of it. Okay. Now you put another metal line, you can see that the height differences per layer is increasing. So over here the height difference is 0.3 micron plus 0.4 micron, so 0.7 micron thickness over here. Once you have one more layer, 0.7 plus 0.5, 1.2 micron, and then you had one more step, the 2.2 micron height differences start to happen. This is not good because of the fact that as we have learned in 3012, lithography is going to become very, very challenging when you have surface roughness. Second problems you are going to have is this program, this assumes that the film thicknesses everywhere are uniform and you are able to coat things nicely. That is also not necessarily true. Okay, we'll talk about in details in the next few slides. So we need to go from, so this is just a case where you have 3 layers. Over here we are building up more and more layers. Over here there are 5 metal layers over here, and in reality you can go to 7, 8, 9. So you have to manage and start to work on the planarization early itself, such that you can have uniform surfaces being created. So how do we now do, so why do we need to do planarization? So one on the top over there are the equations associated with lithography. If you guys remember from 3012, the resolution, which is the smallest pattern you can form when you do lithography, is proportional to the wavelength and the numerical aperture of the lensing system. So normally you try to reduce the wavelength smaller and smaller so that you can form finer and finer patterns, therefore smaller and smaller transistors, therefore faster and faster phones. However, as you make the resolution smaller and smaller, you also make this depth of focus smaller. So the depth of focus is the ability of the lensing system to project the image of the mask on all parts of the wafer. So let's say this is the wafer, and you have certain parts of the wafer which is this high and certain parts of the wafer which is very low. If the mask has to project the image of if the lensing system has to project the image of the mask on this part and on this part equally well, such that it can do lithography, the depth of focus of the system has to be high. So if you're taking photography, if you're taking a photograph of one component versus 3 components kept separate apart, you have to, it may not be possible to get all the 3 things in focus. Sometimes you can only focus on one thing. If you can only focus on one thing, that means your depth of focus is very small. So if you want to have a proper pattern being generated on a rough wafer with height differences, you need to make sure your depth of focus is high. But a lensing system's depth of focus and the resolution are kind of inversely proportional to each other. Anything that improves the resolution will make sure your depth of focus is small. Therefore, you have no choice but to make your wafer as smooth as possible to make sure that your patterns can be transferred. So you need the lithography, in order to make sure your lithography is doing very well, you need to make sure your films are very smooth. Okay. Other problems that can happen are this kind of pattern. So let's say you have a metal line over here and you have the photoresist spun coated on top of it. When light falls on it, at certain locations there is more light reflection. Over here there is less light reflection when you come from the top. Yeah. And after you have developed the photoresist, you could have this kind of a pattern being generated, because of the fact that over here you have more reflection and over here you have less reflection. So the amount of photoresist that is being developed can also change. Okay. So in addition to the wavy nature that we talked about in the tutorial, these kind of effects can also happen. Okay. And of course the thickness of the photoresist is much higher here, much lower here. This also will bring about variations in the structure, variations in the lithography process. So this is one problem we are having, poor planarity. Okay. The second problem is in the etching part. So this is shown more clearly over here. So let's say you have this metal, let's say you have this SiO2 layer over here, and on top of that, the blue thing is a silicon nitride layer that you have grown. Now when you do an etching, physical etching where it is cutting from the top, on the top it is gone, on the top it is gone, but at these edges, these materials will still remain. This can be silicon nitride, this can be photoresist. Because of the fact that your etching is vertically down, you could have these kind of stringers being created. Now these stringers are useful for us when we try to create the spacer for lightly doped drain and things like that. But if you're having photoresist left over after you have done a process, this photoresist will degrade later on as you build things and cause problems for you. So for etching also, you need to make sure that the topography is more or less flat. All right. And then finally, of course, if your topography is not flat, you will also have problems with filling. So it becomes challenging to fill in the voids between these things, and therefore you could have problems associated with gaps, you could have problems associated with moisture or water stuck in the middle and then causing degradation effects later. Therefore, it is important to make sure we have more or less good step coverage and planarity to ensure less defects in the system. So, there are certain aspects by which you can define the planarization factor. So, beta is equal to 1 minus the final step height divided by the initial step height. So, let us say this is your SiO2 or a metal line sticking out, and the initial roughness of your film is Ti step, and after you've done your planarization is becoming smaller and smaller. This is the number that is given out. Okay. So, if final step and initial step is the same, that means you have not done any planarization, the beta is 0. If the final step is almost nothing, that means the beta is 1 and there is complete planarization. Okay. So, you can see that there are certain terms you can use. Here is partial planarization. So, certain areas are smoother, and in between these 2 points, for example, it's more smooth, but it's not exactly completely smooth. Here is local planarization. So, between these 2 gaps it's more or less smooth. Here also is smooth, but between them it's not really smooth. So, these are not so technical terms, but you can have local planarization, global planarization. You need to make sure you are closer to global planarization than to local planarization. Okay. So, this is the ways to define planarization. So, how do you actually do planarization? These are the 3 techniques for doing planarization. We will talk about deposit and etch back, chemical mechanical polishing, which is the most predominant one, which is spend more time on, and we have also this thermal flow, BPSG, PSG. So, in one of the process flows before, we have actually come across BPSG and PSG, whereby which you would put the silicate glass over it, and then you would heat it up such that it relaxes. So, it's I think in 1 or 2 lectures previously. BPSG and PSG also has advantages of grabbing sodium ions and getting defects and moisture. Therefore, that is one more advantage of BPSG and PSG. However, we will go through this in more details now. So, before that, let us just take a 5-minute break before I continue. Okay, let's continue. So, we are going to talk about three different planarization techniques. Okay, first let's start with BPSG and PSG. Now, above images show you the SEM images for on the left side. Let's say for a phosphate doped silica glass. So it is not silicon, it is SiO2, and phosphorus is added into it. Again, phosphorus is not added to improve conductivity or anything like that. Phosphorus is added to change the glass transition temperature of the glass. Okay, so you can 0%, 2.2, 4.6, 7.2 is the concentration of the phosphorus inside the SiO2, and as you increase the concentration of the phosphorus for the same amount of temperature and time, you have more planarity being induced. Okay, over here is a more dramatic image where you have boron and phosphorus doped silica glass. You can see that this is the initial profile that is being generated, and after you have heated up at 850 degrees C for 30 minutes, it starts to flow and become much smoother. So the planarity of this is bad, over here is much smoother. Okay, so planarization can be done. So planarization can be done with PSG and BPSG. But of course, you can immediately understand what is the problem associated with BPSG and PSG, and that is the temperature. Yeah. So you are talking about 1100 degrees here, 850 degrees centigrade. These are all pretty high temperatures. The implications of this is that you can have dopant diffusion. So your concentration of phosphorus and concentration of boron and phosphorus in these systems are very high. Boron especially is a material that likes to diffuse again. So when you heat it up, boron from the silica glass can actually diffuse into the silicon and cause problems in your devices again. Okay, so the high dopant concentration within the silica glass can induce doping into the silicon. So this is one problem. Second problem is phosphorus can again react with the kind of silicon and other kinds of materials and create a kind of a corrosion kind of effect. Okay, so that is another problem. And the third problem, of course, logically is that the temperature is too high. So the temperature you can see of 1100 degrees and 850 degrees centigrade is so high, it could actually melt the metal layer itself. So thermal flow planarization of BPSG is fine for the bottom layer if your layers etc. are tungsten and things like that. But if you are building and using BPSG in the middle and you have a low melting point metal, you have a problem, because during the planarization process your metal layer will also start to melt, okay, and flow. So BPSG and PSG is useful for the pre-metal dielectric part of it, but beyond that it's challenging to use the BPSG or PSG. Okay, so that's why, so it can even melt the aluminum metal that is required. So we need to come up with different planarization methodologies. This is a more painful methodology but is more useful. It's called deposition and etchback. So in the deposition and etchback process, okay, here you have our, this is a CMOS transistor. So here you have your NMOS, here you have your PMOS, you have your low cost SiO2 below it, here you have your channel stop below it, you have your boron phosphorus doped silica glass in the first layer, you have some metal lines already deposited, it has aluminum, so you cannot use BPSG anymore. And over here you do put undoped silica glass, which is USG, okay, undoped silica glass. First you deposit the undoped silica glass through CVD, and then you do sputtering to change the shape of the material. Then you deposit again the another amount of CVD USG, and then you back sputter again. You continue this process again and again until the film becomes more planar. Okay, so this is a very painful process whereby which you can utilize sputtering etchback or reactive etchback. So as long as the etching is more vertically down or more anisotropic, you can finally end up with a more planar surface. Okay, so this is a deposition come etching, deposition etching, deposition etching kind of process to get back to deposition to get more planar surfaces. So this is a more cumbersome process, but if your morphology differences or your profile differences are very extreme, you could utilize this. This is a more elegant manner. So let's say you have a tungsten metal sitting on top of it, and you have grown your SiO2 layer on top of it. You deposit a photoresist. So since the photoresist is coming from a solution, it can spread very nicely and form a final thickness that is very uniform. Okay. So when you spin coat the photoresist on top, it won't follow this shape. It will have a top surface flatness. Once you have formed a flat top layer, what you then do is you come up with an etching mechanism or an etching procedure which is etches the resist and the oxide equally. So a non-selective etch is utilized. So in this case, let's say you have a high concentration of CF4 and O2, it will etch SiO2 and it will etch polymer almost the same rate. So starting from the non-uniformity of the SiO2, we deposit photoresist which makes the top surface planar, and then you etch back everything with a chemistry that doesn't care what it is etching. After that, you can see immediately after you etch back, you are able to get a more flatter top surface. So by utilizing an etch chemistry which is insensitive to what material it is etching, again you can form a planar film. And once you have formed the planar film, you can build more layers on top of it and continue. Okay. So every planarization process is a very painful process of depositing an etch back or high temperature processing, etc. Okay. The most commonly utilized method now is this method called chemical mechanical planarization or chemical mechanical polishing. It is a very crude like looking method, and basically what you have is a platen. A platen is basically the base layer, okay, holder, and there is a huge polishing pad on top of it, and on top of the polishing pad you have a carrier that pushes the wafer down, touching the polishing pad. The polishing pad is typically made of polyurethane or something like that, and then on top of the polyurethane pad you put a slurry. A slurry is a mixture of nanoparticles and acid or alkali depending on the kind of chemistry you want to do. And after that you put that, you just basically polish it. This is very crude method. It's more like how you wash your dishes and you want to clean off the dirt in your plate, but this is a very effective method. So if you want to try and formalize it, the rate at which you remove the film is proportional to the pressure you apply. Of course, higher pressure, more amount of material, and V is the relative velocity between these two things. Okay. So the relative velocity typically is 5 meters per second, and normally you apply for about 10 minutes. You do the polishing before you let go. So over here you can see if the film, this is the wafer, yeah, and some part of the film is sticking out while some part of the film is flat. When you are polishing against it, at these locations the pressure is higher and therefore polishing would happen over here. At this place there is no pressure, it's not even in contact, no polishing will occur. So it's a very crude process but very effective process at making the film very highly planar. Okay. So this is how a system would look like. This is an older system whereby which you only have one wafer being polished. Now you have big systems with 6 or 8 wafers polished at the same time. You have this slurry dispensing system which literally drops the solution and makes it wet, and this is the conditioning disc. So the conditioning disc is basically a disc which may have some surface roughness normally created by diamonds or hard carbides and things like that, which roughens up the surface of the pad and makes sure that the pad is always in a constant mode. Because you know the slurry can get stuck within the pores of the pad, and then the structure of the pad can continue to change. So if you have the conditioning disc which always makes sure that the pad is consistently the same, you can control the polishing process. Okay. So initially when people were coming up with chemical mechanical polishing pads, they were trying to do this kind of a micro replicating surface or very fancy surfaces which has some ceria, which is a CeO2 material, which has some abrasive quality. This is not heavily utilized now because people don't see the point. This kind of very simple polyurethane pads is utilized along in conjunction with this kind of silica slurry. Okay. So you can see that this is about 25 nanometer or 50 nanometer sized particles based on SiO2, and this is mixed normally with an alkaline solution and then polished using this kind of a pad on top of your oxide. So over here you have, it's written oxide slurry is normally an alkaline solution with silica on it. Alkaline solution means your pH will be very high. Acidic solution pH will be very low. Normally you may be using with aluminum oxide, and you could have other additives inside. So we will go into more details in a bit of a time. Other things, there are many things that go inside the slurry. These are the active components of it. You could even have bactericidal solution, bactericidal materials added inside so that bacteria and fungus don't grow in the solution. So all kinds of stuff goes inside here, but this is the most active material, this slurry and this polyurethane pad. So now let's look at the examples of oxide slurry and a metal slurry. So when you are trying to polish away oxides, so the bottom is the SiO2 surface. Because of the fact that we are doing in an aqueous condition under alkaline condition, the SiO2 surface or the silicon surface will have this OH bonds being created. So the top surface of the SiO2 will be actually hydrolyzed by this SiOH bonds. Okay, this kind of SiOH bonds always happens under water conditions or under alkaline conditions. Now your slurry particle, which is also made of SiO2, because of the fact that it is also in alkaline condition, has this SiOH bond on it. Once the slurry particles come and start to interact more carefully, more closely with the surface, this SiOH and this SiOH will bond together to form SiO-Si bond. These kind of bonds are very common even when you use self-assembled monolayers and you assemble chemical organic layers on top of it. This kind of SiO-Si bonds are being created. And then due to the mechanical action of the slurry, you basically break the Si-Si bond within it and pull out the material. Okay, very simple logic. It's like brushing teeth, not exactly like brushing teeth, but basically using abrasion of the slurry as well as the chemical bonding between the SiOH and the SiOH below to pull out the material system. Okay, the more elegant system is the case of metal polishing. So in metal polishing, you not only have the abrasive effect of the alumina particle or Al2O3 particle, but you also have two other components within the chemistry of it. One is you have two components in the solution, one which tends to oxidize the material and one which tends to etch the metal. Okay, so let's say you have the metal surface, you have the abrasive particle inside your slurry. The solution has at least two components. One is an oxidizing layer and one is an etching solution. Okay. Now the problem is if your etching solution concentration is very high or you don't have this oxidation film at all, you can just see that if you have a wet etching solution, it will just etch away everywhere in every direction, because a wet etching solution is not directional. It just dissolves everything in a normal manner. So you cannot just have your slurry have this metal corrosive wet etching. You need to have the metal passivation layer. What happens when you have this metal passivation layer is that the moment you put the silicon coated wafer which has a metal on top of it inside the solution, this kind of a metal oxide starts to form. When the alumina particle comes and hits this metal oxide, at those locations where the alumina particle hits the metal oxide, it is removed. And at those locations, wet etching will start to happen. Immediately again an oxidation process occurs and protects the etching from happening until the particle again removes the the oxide and reveals it. So you have oxidation and removal of the oxide and etching happening all at the same time. So it is more clearer over here. So let's say you are trying to polish off tungsten. Okay, so this insulator is typically SiO2 and you have a tungsten line over here, and the tungsten line has this kind of a morphology. Immediately the moment you dip inside the solution, you have an oxide layer being formed. So the top layer over here is the oxide. So the oxidizer solution within the slurry is iron nitrate, which converts tungsten into tungsten oxide plus H2O. Okay, tungsten oxide is a kind of a hard material and does not get dissolved away so easily. Now when you are polishing it, you know the polishing pad will touch this part more preferentially over this part, right, because this part is sticking out. Therefore, when it starts to rub off, it will remove the tungsten oxide over here. The moment the tungsten oxide is removed over here, the other etching components of the slurry will start to attack over here. But the moment it starts to attack, it will again oxidize. So again this slows down. Again, because of the fact that the pad is touching this part preferentially, the pad and the slurry removes this tungsten oxide, again allowing a bit of the etching to happen. Such and so on and so forth, it continues to happen until the film becomes flat. So because of the fact that tungsten has to be oxidized to form an insulating layer or a more robust layer, the etching solution cannot attack it. So it gets attacked only at the location where the pad comes and removes the oxide. Immediately this wet etching starts to happen. Then oxidation again, then removal of the oxide, then etching again. Okay. So this kind of smart chemistry continues to happen when you are doing polishing. And the reason, and this shows you why we choose the particular type of pH that we use. So this is something called the Pore-Bay diagram. So the Pore-Bay diagram is actually normally utilized in electrochemistry, and you may have come across it in some of your electrochemistry courses. This shows, for example, the kind of different states that tungsten would be in water at different pHs at different applied potential. So in our case, we don't have any applied potential. So you can see that tungsten is stable at different conditions. Tungsten oxide is stable under this area, and you have other types of tungsten oxides also being created. Okay, because of the fact that the tungsten oxide WO2 and WO3 are very stable and won't get etched away in the solution, you have to use pHs which are very slow, which are very small, such that when the iron nitrate is oxidizing the tungsten, it forms this harder to solubilize tungsten. If your pH is very high and you have iron nitrate, it may form a WO42 minus based oxide which gets easily dissolved away, which is not what we want, because if it gets easily dissolved away, it will be chemical etching, it will etch in all directions. We want to form a stable oxide and that dissolution to happen or etching to happen only for a very short period of time. Only then can we go vertically down. So over here it shows you the cross section image of the tungsten via. So let's say you have a hole, you have a via or a trench, and you fill it up with tungsten grown through CVD process. You can see that the surface roughness is there, and then, of course the tungsten is sitting out. But once you polish it off, there is no more tungsten connecting it. Yeah. So here the tungsten layers are all connected with each other. After polishing, this is the top view. The tungsten is only within each of the vias. Okay. So the tungsten solubility and using selective oxidation and etching of the tungsten is a way in which you make sure that your films are extremely planar. Okay. So therefore, chemical mechanical polishing has a lot of advantages. Although it looks like a very messy system, very dirty system, we talked about two particular type of logic: oxide slurries and metal slurries. Of course, there are more subtleties and complexities to it, and the recipes for the slurries are very closely guarded secrets. Okay, so every company has their own secret recipe. One of the problems with CMP is, of course, dishing. So this is not exactly the best picture to show it, but it shows you how when you are polishing away, let's say copper stuck inside a via, your copper, instead of just being cut off on the top over here, there is a bit of a dishing, and the copper within the via can also get thinned down. We talked about it in the previous lecture. So copper, let's say you have copper here, and then you have nitride over here, which is a much harder material to polish off. Once you are hitting the limit, copper can still get polished off. This is a case of a shallow trench isolation where, again, let's say undoped silica glass or SiO2 is filled in the middle. Again, because it can be much more softer than the nitride, you have this kind of a dishing effect being occurring. So as we talked about before, we can try to make sure we have dummies, etc., such that the amount of density differences is not so high and dishing can be reduced. Okay. In addition to dishing, one more thing to talk about is erosion itself. So dishing is the problem associated with etching within the plug or within the via. Erosion is for the materials between the via. Okay, so let's say you have a high density material over here, high density of features over here. Dishing can occur, but also the interlayer dielectric or the top layer itself can get eroded. This can happen because of the fact that the interlayer dielectric is also soft. Another problem that is shown over here is some residue and barrier left behind after polishing. Okay, because no other process mechanically touches the surface of the wafer other than chemical mechanical polishing. A lot of defects can happen if you are not very careful with the way you do it. Okay. Other problems could involve, which is not so clearly shown over here, but as I told you, when you have copper, you have to put a barrier layer, etc., to prevent copper from diffusing out. Even if it's not copper, it's tungsten, you normally have some barrier layers, and those barrier layers also have to be managed very nicely, because the polishing rate of those barrier layers may be very different. So you need to make sure that the barrier layers don't cause additional problems for you. So all these, this non-homogeneity on the top surface of the wafer can be a problem when you're doing chemical mechanical polishing. Certain places you'll have more metal, certain places you'll have more nitrides, etc. So you could use chemical mechanical polishing at only certain steps. So over here you used PSG at the beginning, and then once you put metal lines on top of it, you go to chemical mechanical polishing. In this kind of condition, you can see this is not so great, because let's say I have filled in the holes and I have created the vias. I have two different depth vias. So I need to make sure that my etching to create this via is long enough, but over here the etching would have happened very fast, and therefore I need to make sure that there is a etch stop over here that allows me to etch, prevents additional etching at this location while allowing me to etch this one. Okay. Similarly, when you are filling it also, let's say you're using CVD to fill tungsten within this via and within this via, of course this via would get filled up very quickly. So it is better to go and do planarization at the early stage itself, such that you have more control over the processes that you want to utilize. Okay, so don't try to do it halfway, do it early itself. So in addition, problems is including additional problems other than dishing and erosion are these kind of particle defects. Let's say your pad has scratched off or fallen off, that can be a problem. Scratches, of course, can be a problem also. And this shows you what I talked about with respect to the barrier layer and things like that. So this is the electroplated copper. You have the copper seed layer, and then you have the copper diffusion barrier layers. When you are polishing, you need to polish off the copper seed, and then you will run into polishing the tantalum or tantalum nitride. Depending, because tantalum and tantalum nitride are conducting materials, you may want to polish them also completely off. But now the chemistry will be different, because now this is a metal and nitrides are harder to etch off and polish off. So you need to make sure that all these considerations, all these factors are taken into consideration, and you tune the conditions more carefully. Another factor I forgot to mention is here. One more factor that is measured here is the IR probe, which measures the overall temperature of the pad itself. So if your pad temperature starts to rise or start to drift, again the chemistry of the etching can modify. So you need to have good control over your temperature of polishing as well. So we talked about the chemistry of chemical mechanical polishing, we talked about the problems of chemical mechanical polishing, and we talked about how we need to consider the different layers that we are polishing when we are trying to complete the chemical mechanical polishing. Okay, so so these are the kind of factors that are important. You need to make sure the liner issue. So let's say you are polishing tungsten and there is titanium nitride and titanium below it. You need to, it will etch very, very slower, so you need to continue to polish. But below this titanium and titanium nitride would be an SiO2, so you need to make sure you don't etch off the SiO2 also. So these are the different factors that are important. Because of the fact that you have a lot of acids or alkaline acid solutions inside when you are doing the metal etching, that could induce some electrochemical reactions between the copper and the barrier. So you need to be careful of that and things like that. And these are just an illustration of a couple of problems that could happen. Okay. So now, so chemical mechanical polishing is sometimes called the dark art because it is very hard to, because there are too many factors that come into consideration. So every process needs to be individually optimized. Every profile, depending on the material systems, etc., has to be very importantly considered. So the factors that are the inputs or the problems or the factors brought in by the wafer itself is the size of the wafer. A 6-inch wafer and an 8-inch wafer and a 4-inch wafer will be different. Wafer curvature, if there is a bowing of the wafer, the pressure applied on each part of the wafer would be different. If your materials are harder at certain locations, softer at certain locations, they'll be different. The coating thicknesses would matter a lot. Coating thickness variation and the geometry of the pattern itself. And in terms of the solution, the pressure you apply during etching is CMP is important. The relative velocity is important, so you kind of fix it. Temperature needs to be controlled so that the chemical reactions are controlled. If the number of particles are higher, then of course the passive oxide removal rate as goes up. The slurry needs to be refreshed such that the pH doesn't change so dramatically, and of course your pad will eventually wear off. So you need to maintain that properly, and of course how long you etch it. So these are all factors need to be considered, and therefore of course you have random variation also. So let's say your CVD guy did not control his process very correctly, and the tungsten now has a fluctuation of plus minus 10% or plus minus 15%. Of course, the CMP has to compensate for it. So all these kind of random factors will also come in, and therefore you need to really go and optimize the kind of processes that you utilize for CMP for each pattern. Okay. So these are all the factors involved in CMP. So based on these conditions and what we have learned today, we go through a back end of the line process flow. This process flow is very, very dense and contains a lot of things written in one picture and one picture. So don't get confused, etc. Just try to get the general sense of it. Okay. So again, we have our CMOS device. So we have a PMOS over here and NMOS over here. Instead of low cost, we have shallow trench isolation, keeping the devices separate, and we have our mask, our gate stacks over here and here. Okay. First step is we deposit a thin layer of silicon nitride. Silicon nitride is a very robust material, does not allow for much oxygen and water diffusion. So we first insulate using silicon nitride, then we deposit our PSG, okay, phosphate silicate glass. In this case, we are not going to do much planarization by heating or anything like that. We are just going to CMP it and form a flat film first. Once we have formed a flat film, we do the first masking. So we do photolithography, open up the mask, and we do the etching of the USG to open up these contact locations. Then we deposit a titanium layer to form the contact, then a titanium nitride between the tungsten and the titanium. Okay. The reason why we put titanium nitride is again to improve adhesion. One more factor is when we are growing tungsten, we sometimes grow tungsten through CVD processes using tungsten fluoride and those kind of conditions, and you don't want your tungsten fluoride to react to the titanium. So you put another layer in the middle. So you have put the first metal line down with tungsten, and then of course after you have deposited tungsten everywhere, you are going to CMP the tungsten away such that the tungsten is only at these locations. Okay. So look at the color, the dark brown, dark gray color tungsten, which was everywhere, has been CMP'd away. So we only at these few locations. Okay. After we have put the tungsten, after we have CMP'd the tungsten away, we deposit trench stop and then an interlayer dielectric. Interlevel dielectric is the material system that keeps all the metal lines separate from each other, and you try to make sure that the dielectric constant of these materials are very low. Okay. Normally we want to make sure that the dielectric we talked about only in the transistor, where we want the dielectric constant to be very high to turn on the transistor. In this kind of ILD of interlayer dielectrics, you want your capacitance to be very small. because of this problem called RC delay. Professor Puisi will be talking about RC delay in more detail. So this kind of interlayer dielectrics can be silicon oxide which is modified to bring down the dielectric constant and things like that. Okay. Once you put this interlayer dielectric, now you pattern the interlayer dielectric. So you can see that this interlayer dielectric is now modified. Now you start to deposit, you use the mask that is for forming the first copper layer. You etch your interlayer dielectric from the pattern. You deposit your tantalum nitride copper barrier to make sure copper doesn't diffuse in. Then you deposit your copper seed layer. Okay. After you deposit your copper seed layer, you dip inside your electroplating solution and you electroplate the copper everywhere. After you have electroplated the copper, you annihilate to make sure that the copper is of the right morphology, and then you will start to polish this off, which is shown over here, where you again have the copper sticking out. Here now the copper is polished off, and then you have cleaned up to form the first layer. Then you start to again put additional via stop, interlayer dielectric, trench stop, intermetallic dielectric. In this case, you etch through two dielectrics together to deposit one metal layer. Again, after you have etched through the two dielectric locations, you again clean out, you again put a copper diffusion barrier, you again put the copper seed layer, which allow you to electrodeposit copper on top of it. Then you dip it in solution again. So that is the electroplated copper here, annihilate it again and continue and you build up layer by layer. Every time you deposit copper, before that you need to put your diffusion barrier, your seed layer, before you electrodeposit and anneal the copper. Okay. So by this connecting up layer by layer, you can make complex circuitry connected to each other, and this is why I say you have kilometers of metal lines inside these devices, because they are really complex. So you need to make sure that you don't have defects anywhere. Anything can go wrong at any location. Not anything can go wrong, but these are the problems you could have. One is, let's say you are electrodepositing copper in the vias over here. You could have something called a seam, which is, let's say, an area in the middle which is not completely deposited. So that could create high resistance at these locations. If your copper adhesion is not good, you could have a problem. If your tantalum nitride or layer copper diffusion barrier is not so good, copper can diffuse in and you can have problems. You could have etch residue when you are doing the etching and forming these layers, which can again cause problems. Because at each point on the CMP, on the copper, you are doing chemical mechanical polishing. If you have a scratch or something like that, that can cause problem for you, so on and so forth. So at each point, you normally do in-site inspection to make sure that your process is continuing on nicely. At each point, you would have some kind of a test structure which allow you to check the quality of the copper that is being formed at each layer. So just like you have this device, you may have a test structure which is defined and only formed at this point, at, let's say, at this copper layer. So let's say just like you have this patterns over here, you may have a rectangle or a triangle, a rectangle or a test structure made of the copper grown over here or grown over here, and during the inline inspection you would check that quality of the copper. Okay, so in that way you can try and make sure that your devices are functioning and the layers you have deposited are accurate. Okay, so this is with this lecture we have talked about everything up. Previously we had talked about everything below. So we will, both the knowledge of both these areas are important to understand the whole of microelectronics. Okay, so today we specifically looked at electromigration. Electromigration is the effect of whereby which you have momentum transfer between the charge carriers and the ions, and that can lead to the breakage of wires or to the formation of kilocks. This is the primary reason why we went from aluminum to copper. And the other advantages of copper are copper is much more highly conducting compared to aluminum as well. Okay. In order to the problems of copper is that we need to develop a new patterning process to pattern the copper, and that is called Damascene process, whereby which we create patterns within the dielectric, fill it up with copper and then polish it off. In order for copper to be utilized, other factors that include not only Damascene process, you need to make sure you have diffusion barriers also. so that copper does not diffuse into the silicon. And because we are trying to fill in vias now for copper, you try to grow it through electrode deposition process. Okay, details of the electrode deposition process will be talked about by Professor Lippoisi. All right. After we have, so this is the logic in which we form the metal lines. From aluminum we have gone to copper, and then this is the way in which you build layer by layer on top of the transistors. The biggest problem is non-planarity. If your films are not planar and there is surface roughness or non-uniformity, this can cause problems of lithography, this can cause problems of filling, and this can lead to residue when you are etching. And we talked about 3 different ways to solve this problem, which is by reflowing the BPSG or PSG, deposit and etch back, and chemical mechanical polishing. Reflow, the problem is that you have so high temperature, so high concentration of the dopants, this can dope the underlying silicon. More importantly, the temperature is so high that you could lead to the melting of metal and things like that. So you go to other conditions. Deposit and etch back is a very painful process, which can be utilized, but now people have more or less switched completely to chemical mechanical polishing. Chemical mechanical polishing is a dark art. You can have a lot of problems, you can have a lot of variation, but in general, if you have once you have controlled your process very nicely, it gives you good results. We talked about oxide chemical mechanical polishing, metal chemical mechanical polishing, and then we talked about the particular problems of erosion and dishing within the chemical mechanical polishing. And finally, we went through a copper based process flow where we show how we can build up multi-layer structures by doing the process one by one. Okay. So the process flow is primarily for you guys to get an understanding of how a layer is being built up. As long as you get a sense of it, you don't need to worry so much about the details of this particular process flow, etc. Okay, that's all I have for you today. Thank you.